Welcome to another exciting finite element modeling tutorial. Today we'll be discussing the fatigue analysis of an aircraft wheel. And today we have an invited lecturer, Eddie Chen, that will guide us through that tutorial. But for now, let me remind you what fatigue is about. Fatigue is induced by cyclic loading conditions and is an important consideration in the design of aircraft designs. So if the load is varying and there's fluctuations in the load, the repetitive loading condition will cause something called fatigue failure. And it could be induced by low cycle fatigue or high cycle fatigue. Aircraft wheel is an example of fatigue critical application where cyclic loading conditions could occur from not only the hard landing they could experience, but also the tire rotation. As the tire rotates, the wheel will rotate and the stresses will vary around the circumference. And at any given point in the wheel, that stress is going to go from a low value to a high value and back and forth. And that's your repetitive loading condition. And this tutorial will illustrate the modeling techniques for aircraft wheel analysis. And the conditions of the problem that will be discussed in the tutorial are different from what I'm going to discuss here. But what I'm trying to provide you with is a top level view of what we're trying to accomplish. An airplane wheel rim typically will have a shape like this, and it will have holes around the circumference of the rim. And the purpose of those holes is to allow for an optimized weight design, but also to allow flow that will allow cooling of that wheel so that during operation it doesn't overheat. The conditions of the problem during the tutorial may differ, but the bottom line is a light aircraft of weight 5,100 kilograms is provided. And we're going to assume that that weight is distributed across all three wheels. We're going to ignore the rubber tire that will typically be surrounding the rim, and that's going to be conservative. Now, the rubber tire will absorb all the shock from the hard landing, but in reality, all that load will have to be transmitted to the rim. What the rubber tire will do is to distribute that more uniformly around the rim compared to how the analysis will be done in this tutorial, which is fine because it's a conservative analysis. And the analysis of rubber tire in itself is complicated. It involves considering hyperelasticity of the rubber. So you have to get those material properties, and that needs to be simulated also within this context of the wheel analysis. But for now, we're going to ignore that portion and only design the rim. In the tutorial, the conditions may vary, but typically you have the density, the Young modulus, the Poisson ratio, and typically you will determine the fatigue curve from either experimental data, in-house experimental data, a reliable source such as MMPDS or Mill Handbook 5, or a MatWeb, for example, or the Aerospace Metals Handbook, for example. On the right side, what you see is the information that can be provided to ABAQUS, the stress strain curve, and in here, what you see is the yield stress and the plastic strain corresponding to that. In the analysis, we will be simulating a hard landing. Now, you could have multiple hard landings. We're going to assume a friction coefficient 0.3, and we're going to assume that because of the hard landing, you're going to have a 3 times G, so 3 G's of that wheel hitting the ground. And so that's what we're going to be looking at. And what is the max stress that's induced on this rim by that condition? We're going to also look at the tire rotating on the ground. And in here, we're going to assume a 1.5 G condition that's conservative, because once the aircraft lands hard, you will expect the aircraft to dampen out through those tires down to a 1G condition, so then the aircraft travels through the runway. But the idea here is how we will consider this condition plus this condition. And you have to look at the stress state at every hole over time and trying to determine, given the number of cycles that you will see in service, what is a life and how to design this tire so it can survive the life for which you're designing this wheel for. We also want to look at how many rotations will this rim make to reach fatigue life. So assume LCF, low cycle fatigue, is not considered. You can use the SN curve for that. For low cycle fatigue, we can look at how long this wheel will endure the landing and how many landings can this rim take if the high cycle fatigue is not considered. We'll then have to use the strain life relationship for this analysis. And how about the combination of life cycle fatigue and high cycle fatigue analysis? You'll have to use Minor's rule to evaluate life. That's the hint I'll give you, and I'll let you think about it. Take it over, Eddie Chen, for the tutorial, and I appreciate you coming in as a guest and providing us this great tutorial. Appreciate that.
First, we'll start with the airplane wheel rim. We will draw this on the ABAQUS interface. So first, start with part and to create a part, and the rim is 3D deformable and is solid. There are three ways to generate a part, and we will use revolution for the ring, and the approximate size is 400. So this is quite simple. Just follow the point on this picture and use this icon here. This is the inner part, and then this goes to the upper part. Then we draw these two straight line here. And you use this icon, you can generate a round corner. So what you can see is the upper cross section of this ring, and the software will swipe it 360 and create the 3D model. So next step, you'll need to define the rotation line for this web. So I'll use the axis as the rotation line. So we're done, and click the button here, and then you will need to select the construction line. That's the center line for the rotation. So it's this one, and the angle is 360. So yeah, here's the rim.
So after we finish the rim drawing, we also want to create some holes on it to absorb the energy during landing. And how can we do this? Here, this icon, create cut, extrude. Click this and select this surface, and then select this line here, and you'll see the same interface again. And first, draw a circle. This circle will be where those smaller circles are, and change it to 96 millimeters. Then draw a smaller circle here. And 10 millimeters. So here we only have one circle. What can we do to create a lot of circles on this larger one? Here we have this icon. At first, you click on it for a longer time, and you'll see two kind of icon in here, and we want to use this one, radial pattern, and then select this smaller circle and done. And then you can decide how many circles do you want on this rim. So I'll create 6. Okay. After this, we'll need to delete the larger circle, and the delete is this icon here. Done. And then these are the holes we want to create on the rim. So press down again. And then here, this is the way you want to extrude these 6 circles. And here I will choose this way, blind. And type in the depth, and which should be long enough for these circles to penetrate this surface. So yeah, 100 should be enough. And press OK. So yeah, we have our circle here. Oh, sorry, we have our holes here.
So in this model, we will need a ground surface for this rim to contact with. So we'll need to create another part, use the same icon again. But this time, the ground is 3D, but it's a discrete rigid because it's not deformable. And then we will use shell element to increase the calculation speed. And the drawing type will be extrusion. The radius of the rim is 150 millimeters. So the ground should be placed 150 millimeters below the x-axis. So I'll give it a 200 millimeters wide. And 1,200 millimeters long. So this is our ground. After we draw all the parts we need, let's go to the next step. These are some description of the problem. So the aircraft weight 5,100 kilograms, and it's evenly distributed to 3 wheels. So it's 1,700 for one wheel. And the rubber tire is ignored. And so it means that the rim directly contact with the ground. And the rim is made with, is cast by aluminum alloy A356 and with T6 heat treatment. And these are its properties: density, Young's modulus, Poisson ratio, and plastic deformation, and the fatigue curve. So let's put this all into the ABAQUS. Go to the property and create a new material. A356 T6. First density, and then elastic, and then plastic. And here you need to be careful for the unit. And I have one picture that is very useful. Because ABAQUS doesn't have a certain unit system, so you will need to consist all the units you use. For example, I'll use this unit in this column. So the length of all the units should be millimeters, and force will be Newton, and mass will be ton. And yeah. Yeah, that's all we need for the material properties. After inserting the material property, we'll need to assign a property to to the rim. So go to part 1 first, then use this icon and select the rim and assign it to section 1, which is our A356 material. Yeah, and if you assign it successfully, the color will turn into green. And for our floor, because it's rigid, so we don't need to assign any property here. But here we will need to give them the reference point. And for the floor, I assign this point as its reference point. And for wheel, usually the reference point will be its center here. Yeah, reference point means the you can assign some loading or some boundary condition on it, and it will represent your parts. So you don't need to pick up a surface or a line to assign all those boundaries or constraints or loadings. It's very convenient for the following setting. For the floor, although we don't need to assign a material property for it, but we need to assign inertia. It's point mass and inertia. And we can use the reference point we assigned for this one. And for this example, because it's a floor and it's rigid, and so you can give them some symbol value for the mass, the inertia, and it doesn't matter at all. This number will just prevent some errors happens. And for dynamic analysis, this is important step for you, assigning the inertia. It's from the icon here, special, inertia, and manager, and create one. So yeah, that's the property part. Then the next step, we can put all these two parts into assembly. First one is our rim dependent, and another one is the floor dependent. And here, the rim is not does not contact on the surface of the floor. It contact on the edge of the floor, and this might cause some problem in the contact simulation. So we'll need to move the floor a little bit. Use this icon here, translation, and pick the floor, and then select 2 point. So the floor could move backward a little bit. So now the wheel will contact the surface of the floor, not the edge. Yes, and yeah, then that's the assembly. Next, we'll go through the step. And let's take a look on our problem first. We have two steps here in our simulation. And the first one will be hard landing. We assume that the aircraft vertically lowers down and the ring contact the ground, and it takes 3 times the weight. And this is the hard landing. The ring doesn't move and goes down vertically. The second step is that the ring goes around the circumferences. And we simulate it conservatively. We want to simulate this conservatively with we assume that it still take 1.5 times weight during the rotation for 360 degree. Yeah, these are our two steps. So let's input these two steps into ABAQUS. So create step. Step 1 is hard landing. And it will be a dynamic explicit calculation. And time period is 1, and this one should be on because it will have some displacement. And step 2. After hard landing, and it's also a dynamic explicit calculation. So here are our two steps. Then we can set up the interaction. The main interaction will be surface contact. So create interaction and use this one, surface to surface contact. And first surface will be our master, is our rim. So pick this surface. And the second surface is the safe surface, and it's our ground. It's a surface. So and pick the ground. And there are two choices. And this means the normal of this surface, and the one we're gonna contact with is in color brown, color purple, and the other side is brown. So we'll pick the purple. And we'll need to create a contact interaction property with this icon here. So contact. And what we need are tangential behavior and normal behavior. And for tangential behavior, we need to change it to penalty. and with friction coefficient of 0.3 here. And that would be all for the contact. Then the other one is this one, constraint. So we'll need to set up a constraint here with coupling. It means that so we will need to select the point for this constraint, and that is the reference point. And then we'll need to pick up a surface. We'll pick the inner surface of the rim. This means that all the boundary conditions, loadings, and we applied on the reference point will distribute to the purple surface we select. And this will make our following setting easier. And we also, this one is for the reference point of the rim. And we also have another reference point for the ground. So we'll do this again. But this time, it's a ridge body. And the ground is a body, so we click on body and click this icon here and select the ground. And then here the reference point, click on this icon and select the reference point. And then okay. So these are the interaction. And then we can go to load. Okay, let's take a look at our questions again. In the hard landing, the rim will take 3 times the weight, and the aircraft is 1,700 kilograms for one wheel. So 3 times will be the same as the total weight, 5,100 kilograms. So the load on this rim will be 5,100 kilograms when hard landing, and because this is we need to change the unit from kilogram to Newton. So create a load, and this load will be in hard landing step, and it's a concentrated force. We apply it on our reference point of the rim. And is in the minus y direction. And we don't want to apply this force directly at the beginning, so we'll need to change the amplitude curve a little bit. So click on this item. And when the simulation start, we'll start from 0. And when the when it goes to the end of this step, it will be 100%, which is 1 of the total force. So this is a linear relationship from 0 goes upper until when the simulations time reach to 1, it will be the number we want to assign. So okay, and remember to change to the amplitude we just set. And okay, and let's take a look at the load manager. So if we set up a load at the hard ending step, it will automatically apply to the following step, which is the ghost rotation. But in the rotation step, we only want to apply a half 1.5 weight times weight on the ring, which is a half of the loading in the first step. So this one will be too large for the second step, so we'll need to deactivate it. And for the second step, we'll need to create a new one. And the step will be the goes around, and is concentrated force. And pick the reference point again. And this time will be 1.5 times weight. So it's half of the number here. And for the amplitude, because we will simulate its rotation. So during the rotation, the ring should take this whole loading in the whole for the whole time. So we don't need to change to the linear amplitude we just set up. We'll we'll stick to the original one, so the force could apply at the beginning. So okay. Next, the boundary condition. And the first one will be pretty straightforward. It's our ground, and it should be fixed from the beginning. So initial step is initial, and the type is symmetry. Then pick the reference point of the ground, not the whole part or whole surface of the ground, because we have already assigned this ridge body to the reference point. And here, if you select the whole body for the boundary condition, you may not get a proper result in your simulation. So remember, you will need to pick the reference point and all fixed 0, 0, 0. And next one will be the rim. And in hard landing step, we assume that the aircraft lands vertically. So we don't want the rim to move in the wrong direction. So we'll need to fix its displacement. And in hard landing step, and the same as the ground, we'll need to pick the reference point of the rim. And it will land in Y direction. So we don't want it to move in X and Z direction. Okay, here, same as the loading. If we create a boundary condition in the hard landing step, it will automatically generate in the next step, the rotation step. But in this step, we will need to rotate our rim. So we don't want to fix it. So here, deactivate it. Yeah, so we will create another one for the the second step. Is displacement and rotation. And the same, the rim, reference point of the rim. And for this part, the rim rotation can be treated as this item goes forward in Z direction for the length of its circumference. And at the same time, it rotates in X axis for 360 degree. So its circumference is 942.478. And 360 degree equals to 6.2319 radians. And here, this ring does not move immediately when the simulation begins. So the amplitude will use the one we set earlier. It will gradually move to this distance and this angles. Oh, and it's in the second step. So we can, if we set in the wrong step, we can use the icon here and move it to the right one.
Next step will be meshing. And now here we have the whole assembly, and but we want to mesh each part. So here we go to part and pick the rim part. And before you mesh, make sure to assign a mesh control. And now we have what is this color? We have this color, and yeah, select the ring first. And this kind of color is bottom up element shape. And but the best one will be the structured part, and it will be in green color. And also you can use the swept the swap one in yellow color, and now it's unavailable because we did create this model with swap, but we create some holes on it, so we cannot match this part with this kind of selection now, the swap. So we will have to change to another kind of element shape, which is tag and the free mesh. It will be the color of pink. So after you press OK, the element type will change to tag with free mesh, and the color will be pink. And next step, see the part. Here I will apply a finer mesh. I'll say 5. Okay, and then generate meshes. So after this step, you can take a look on the element type. And here we have it's an explicit calculation, so it's a little different from the project one. So yeah, so we finished the ring part. Then we go to the our ground. So first, the same, assign a mesh control. And here, like I said, the best one is structured in green. So yeah, pick this one and OK. And then see the part. I'll also use a 5. And then mesh. And then take a look on the element type again. Yeah.
Job. You'll just need to create one and press OK. And yeah, that's it. And it's ready to run.
So if your task is finished and you press the result button, you'll see this windows here. And for now, it still looks like the original model. And how can we see the result? We can press the icon here, plot deform shape, and it will show the last step of your simulation result. And how to see the whole process of your simulation of remember our setting is that from 0 to 1 second it's hard landing, and from 1 to 2 is rotation. And now it seems like it's in the rotation part. And how do we go back to the hard landings? So you can click here's there's several ways. You can click on the icon here, previous, and it goes back to the first step. Or here, friends selector, and you just need to pull this bar, and you can go to every step you want. So let's see the result of our hard ending simulations. And so now we're at 0, and the ending time of hard ending is 1. And with the step time increase, you can see the stress goes up. And here's our hard ending stress distribution. You can see that there's some stress concentration near the hole. And that's why we said that these holes can absorb energy during landing. And the result now shows the Vomesis stress. And how do you change to other kind of result stress, like principal stress from here, this column. And now it's Vomesis, and you can also go to the maxima principle, and it will show the result of the maxima principle stress. And also there's other choices like Trissica or stress in a certain direction. And for this column, it means the symbol for S means stress, and there are also other kinds of result here, like plastic, and U for deformation. And you can pick the result you want here. Like here is magnitude, and you can also take a look at X direction, Y direction, Z direction displacement. So let's go back to a stress. And the rotation part, you can see the rim did rotate to the front. And for here, I also want to introduce a very useful icon. Is this one, Animate Time History. And if you click on this icon, the whole simulation will shows in this animation, from hard ending to rotation. And if you feel it, if you think that is too fast for you, and you can click on this icon, and for here you can change the animation speed and to make it slower. And for this one, you can also change how them what is your time increment? Like now, the time increment is 0.05 step time, and if you increase it higher to a higher number, some of the result will skip. Yeah, that's it for the ABAQUS tutorial. Thank you very much.